Thank you very much, Uroš. First of all, also really thanks to you and your team for inviting me to give a talk between this very distinguished set of speakers. I feel very honored. Also, the bar has been set very high in the morning, so I hope I can give a talk on hopefully a close level. I also want to apologize in advance. So I'm giving a talk of an hour and a half, and I do not really have any practical sessions. My talk will be about measuring variability in human movement, theory and methodology. So I will, in the first part of this talk, I will talk about theoretical concepts about the understanding of variability in human movement. And then, and this is a bit of my practical, I will show how you can analyze the data, especially the time dependence of the data in terms of the dynamics. This is something that's being done previously in other studies, but I also want to show, and this, it always sounds very complex to do it, but in fact it's not so much. So I want to show the steps of the algorithms, how they are being done. So I'll try and spend like half an hour on this one. You already introduced me. I'm Julian from the Department of Neuromotor Behavior and Exercise in Münster. And yeah, this doesn't work. Or does it? Yes, perfect. And it's after lunch. You may be a bit in a tired mode, or maybe you just went for a swim, so you feel better. But I want to get started with a little question, and I hope you can all try and give an answer to it by raising your hands if you take one or the other position. And maybe I can also ask afterwards if you can elaborate a little bit on your position. So be sure you choose wisely which position you take. And this is the first question is a little bit, not very well posed because there's many different angles to it. So I know that, but it's very general. Do you think variability in human movement is a good or a bad thing? Okay, so can everyone who thinks variability in human movement is a bad thing raise their hands? One person. Perfect. 2 person. 3. Thank you very much. Can everyone who thinks it's a good thing raise their hands? And I'm assuming there's a couple of undecided people as well. Can you maybe elaborate why you think it's a bad thing? You raised your hand.
So is it working? I think it's bad because we are measuring that while like walking, for instance. So you don't have, we are asking for a constant pattern, and you see like people who are like struggling with walking that you have huge variability, and this was kind of like indicative also of the future falls. So it's kind of like, depending on the, of course, the population that you're looking at.
Yeah, absolutely. I fully agree. So if you look at certain populations, you find an increase in variability, gait patterns, and so on. So this is a signature of their disorder or symptom. And who thinks it's a good thing? I think Antonio, I talked with him yesterday, or Voiko maybe, but I talked to Antonio yesterday, and I think he's, so I'd like to.
There is no science without variability.
There's no science without variability, right, perfect. Exactly, and what's your take on it, Antonio?
I think variability allows for flexibility.
Yeah.
So a variable system is also more likely to be able to adapt, especially in a dynamic environment.
Yeah. Okay. Yeah, so I guess you can give my talk now. So,
I was the only one because you need to come to
so my second question, and it's a little bit in line, and we just talked about it. Do you expect a healthy person to move more or less variable than a person with a motor disorder? And again, my question is, do you think a healthy person moves more variable than a person with a motor disorder? Who can raise their hand? It's a bit different now. So I see 3 back there. And do you? No, now the question is, do you think a healthy person moves more variable than a person with a motor disorder? Okay, I see 3 people. And who thinks a healthy person moves less variable than a person with a motor disorder? Only a few, okay. But yeah, so we elaborated that movement variability is a good thing, but we've also seen that some people still think, even though they say it's a good thing, they also think that people with a motor disorder move more variable. And I think the answer is yes and no. It depends where you look at it, how you look at it. So the goals of the talk I want to give today is, or my teaching goals is for you to understand, the time is not running, I see that, but hopefully I just be in time. Is for you to understand the functional relevance of variability in human movement. So we just said it can be used as a measure of performance, but it also points to things like the system being adaptive, being flexible. So this is sort of the functional variability, the functional relevance of it. Or variability is a signature of this adaptivity and flexibility in human motor control. I want you to learn the basics about the theoretical foundation, and this is basically the complex systems theory we're talking about. So I have a couple of slides, and I hope I'm not spending too much time on that. And last but not least, so this is in the last 30 minutes hopefully, I will talk about a few methodologies for the analysis of the temporal variability structure and that have been used in motor control research, and that can be applied, for example, to gait dynamics, to center of pressure data, and so on, and they have been used extensively for several decades now, but I think they're still not used enough. So why are we measuring movement variability? As Uroš just said, we use it as a measure of stable performance in a repetitive task. Take, for example, the example of upper limb reach and grasp task. So we very well know how to reach and grasp a glass and like move it to our mouth and drink from it. So this is like a well-known and overlearned task. If we go to bar late at night, like we do that a lot, and then we practice and practice to become very good experts at this task. And eventually we get like a little bit of a cerebellar poisoning, and then the performance deteriorates. But generally we think we become an expert at a task, and hence if we repetitively execute it, it's very similar. The pattern there is like a motor program ingrained in our head, and this leads to a very similar execution of the task and when we repetitively execute it. On the other hand, we think that if we can't do it very well, then there's a lot of variability going on, or with aging and disease as well. In the same vein, we use it as a measure of steadiness in cyclical tasks and oscillatory tasks, such as gait. We assume that good gait performance or low variability is a measure of good gait performance because we have a clear and we have very little noise in information processing. We have very little we have very good and healthy systems, so not a lot of things happening. So the sensory motor processing works perfectly fine, very little variability. This is our assumption. And third, we use it, for example, as a measure of performance in feedback control tasks. For example, in postural control, I stand on a force blade and just have a look at how how large the magnitude of the sway is. So in these terms. And our assumptions, and this is what I just said, is that an increase in the variability may reflect deteriorations in sensory motor control systems and aging and disease. You're right, a lot of studies show that older adults have more variability in gait, people with disorders have more variability in gait, and so on and so on. So this increase in variability may reflect deterioration of the sensory motor control system. We can measure it, we can check, for example, if certain therapies are successful by measuring the variability, and so on and so on. Also, when we experimentally manipulate sensory motor processing, for example, through secondary tasks, we find an increased variability. Claudia showed it on her slides in the driving simulator. Of course, there's larger deviations, mean deviations. There's also larger variability of the deviations, and yes, this happens when we experimentally manipulate, for example, sensory motor processing. And then we use movement variability as, for example, a prodromal marker for the development of motor disorders. We assume that we can perhaps detect at an early point already if a motor disorder is being developed. There we go. So how do we classically measure variability in motor control? This is something we just talked about. So we use measures of dispersion, so statistical measures of dispersion, such as the standard deviation, for example, in COP data. So we have on the right-hand side, I'm using my pointer now. Should I switch to pointer or should I just use the mouse? Okay. So hopefully you can the people on YouTube see the mouse, but so what we can see here, this is the COP trajectories of one of my students during a seminar. We measured some COP in anterior-posterior direction and in medial-lateral direction. That was eyes open, standing in two legs. We have a large deviation in anterior-posterior direction. We have not so much deviation in medial-lateral direction. And we used the standard deviation around the mean point as our fixed point to make an assumption about how variable this sway is. Yes?
Can I just ask you to elaborate a bit more, because I'm not sure if everybody knows what COP and plate is.
Oh yeah, okay, sorry, yeah. So well, I have pictures later maybe of of a force plate, but what they basically do is they stand on a force plate. We measure their center of pressure, so where basically it's not a direct measure of the projection of the center of mass, but it's very much related to the center of mass. So the center of mass is projected, and when we sway around, when we move around on the force plate, of course our center of pressure. So this is the mean vector of the pressures of all the measurements on all the sides. So if I stand perfectly still, the center of pressure is directly under my center of mass, somewhere here. Down there. And if I go forward, my center of pressure is moving forward. If I go backward, my center of pressure is moving backward. And yeah, if I'm moving around, this line is moving around as well. And we just pick some, we calculate the average, and then we compute the standard deviation in both directions. This has been done a lot. And if we have a larger standard deviation, then there's more sway going on, or like an increased magnitude of the sway. And then we also compute the coefficient of variation, for example, for gait data. So this is also some data we've collected in a seminar where we have just a healthy person walking on a treadmill, and we measured the stride duration for every gait cycle. And we see they have like 150 gait cycles, so there was like 3 minutes. Ish. So yeah, they're walking for 3 minutes. And you see that there's some variability going on. I can use the mouse again. In between here, we have a mean stride duration is 1 second and 1 second and 12 or something like that, and we measure the variability of this. And in older adults, we find that there's an increased variability. And third, this is from a force tracking experiment where people had to produce a certain force and stick to a target force. So we gave them a target force on the screen, and we gave them feedback about their actual force also on the screen, and they had to stick, they had to squeeze 2 little force transducers, had to stick very close to this target line. One is doing a sine wave, the other one is doing like a constant force production, and what we can measure is either the complete deviation, like the root mean square error from this target, but we can also measure the variability of this error. Because they can have a very constant error, they can have a very variable error. So both things may happen. So I want to show a couple of studies that just use these classic measures or measures of dispersion in motor control research. And the first study, and I've been actively looking for Parkinson studies because it's in the title, it's about the detection of postural control in early Parkinson's disease, clinical testing versus modulation of center of pressure. And they had 15 healthy controls, and they had 30 subjects that had Parkinson's disease. 15 of them were in early state, classified by the Hoehn-Yahr scale, stage 2, and 15 moderate PD, Parkinson's disease, classified stage 3. The participants were standing on a force plate, so this is what I just described. Here's the force plate, so this is a plate that's measuring the forces at 4 corners, and if you move around, you can tell what the center of pressure is, of course. And they had the task to stand on this force plate barefooted for 30 seconds, quiet standing with their eyes open, and 30 seconds also with their eyes closed. And the outcomes were the COP range, so that's the difference between the maximum, I again use the mouse, between the maximum up here in anterior posterior direction and the minimum down here, that would be related to the standard deviation, similar, but a little bit different. So outliers are taken more into account. They were also measuring the velocity of the center of pressure movement, and they were measuring the root mean square error of the center of pressure movement. Yeah, the root mean square error of the center of pressure movement is basically the standard deviation. That's the root mean square error from the mean. As a result, what they found, and this I thought is very interesting, is they found significant differences in all COP measures. So the velocity, the range, as well as the RMSE. In healthy controls, those are the bars you see in white, as compared to Parkinson's disease stage 3. So they were all significant. And more interesting, and this I found is really striking, is that did not find a difference between healthy controls and patients at an early stage of the disease onset. So no difference at all. So early stage of disease, so it's already measurable, but they did not find that there's a difference in any of the sway parameters they just measured there. And the interpretation is that moderate Parkinson's disease leads to higher COP excursion. This is something they found. More variability due to greater instability, reflecting changes in the control mechanisms. But this is very interesting, that simple measures of the center of pressure variability are not able to detect changes in postural control in early PD. They did some more in the study, so they found more, but in these classic measures they didn't find that. And this is another study from our lab. It's not published in a journal, so this was only a conference contribution, so you won't find it citable, but we examined the effects of dual task complexity on gait in older adults with and without mild cognitive impairments. In this study, we had a much larger sample eventually, but this was during data acquisition, so at that point we had 35 healthy older adults and 35 older adults with MCI, and we performed a gait analysis on a very short track using an OptoGait system in our lab. And the participants were walking 5 meters down the track, then turning around, walking back. And we had different gait conditions, so they were walking at self-selected comfortable speed. They were working at different dual tasks, using different dual task scenarios, so counting backwards by 1, 3, and 7, so different levels of complexity. And they also used a verbal fluency task where they just named words starting with M or A. And as an outcome, again, I also used just classical measures: average speed, coefficient of variation, average step length, and the coefficient of variation of the step length. What typically happens with the coefficient variation, not typically, but in gait, I think this happens very often, is that they are not distributed normally, so there's always like a, they are left, there's a skewness always in the data, so you have to transform it using log transformation to get it normally distributed, and then we use just the mixed measures ANOVA to compute the results. And what we found is that individuals with MCI, as compared to healthy older adults, showed a little bit slower gait, and shorter step length. That's the difference. That's not significant. No. And they showed an increased variability. So in red you see MCI, in green you see healthy older adults, same age match. And you see that they are, people with MCI have shorter steps, they walk slower, and they have greater variability in there. Although, again, this difference here was not significant with the small sample size, and there's also very large standard deviations, as you can see. And the effect of the dual task type is that we found that the secondary task affects the performance with more complex tasks, leading to higher performance deteriorations. And this is another thing. I thought these curves look very nice, so they evolve very close together. So the impact is very similar on both groups and of the task complexity. Same here, but not so much in the variability measures. But again, this is very small effects. And the interpretation is that in this case, attentional resources are necessary to process sensory motor information in gait. And yeah, that individuals with MCI show therefore a reduced gait speed and step length, and that's basically a compensatory process to adapt to the reduced cognitive function. Right. And one third one, I'll just go quickly through it. So this is from Solveig Filov already 10 years ago, where they had 48 participants grouped as younger and older middle-aged adults, and that made me realize that I'm also now a younger middle-aged adult. Just hooray. It just hits you eventually. Be prepared. Those were also, so this is one category, and nested in that they had fine motor control experts. For example, watchmakers or people who did like precision tasks at work, and novices, so people who did not do precision tasks at work. And the task was to choose a force tracking task and to just produce a constant force level of 2 Newton. And here you can see how this, how such a force like time series looks like. You see that there's an average which is close to, that's just close to 2 Newton. Can I go back? Probably not. Oh yeah, I can do this one. Ha. There we go. So which is close to 2 Newton, but we also have some variability here, deviations from this average force. And what they found is that the group of older middle-aged adults as compared to younger middle-aged adults showed higher variability. And also that experts, as compared to non-expert, had lower variability. So, and there was interestingly no significant difference between the performing hand. And the interpretation that hand fine motor control progressively declines with aging. We can talk about the functional mechanisms later, and the precision work labor has a preservative function, fine motor control, which is very nice. So we do find that what we just talked about, and Uroš's point that variability is a marker of poor performance, variability is bad, we can find that in the data, and that looks very nice. But then again, on the other hand, yeah, there's the standard deviations are high, the effects are small, and it's also very difficult to use it as prodromal marker, for example. So there's more to it, why the standard deviation is not sufficient in these measures. And I have again another question for you. I have 2 signals for you, and this is the anterior-posterior part of the COP data I showed you previously. So this is the movement of the center of pressure in forward and backward direction in centimeters over time. So they stood for 60 seconds, and there was some movement going on. And here I have another signal, the red one. So my question now is, which of the time series displays more variability? So who thinks the blue one displays more variability? I've got 1. I've got 2. Okay, who thinks the red one displays more variability? I got also only 2, and the rest is very undecisive. Okay, I've got another question for you. Which of the time series has the largest standard deviation? So who thinks the blue one has the largest standard deviation? Okay, yes, I got like 4 or 5 people. It's very hard to say. And who thinks the red one has the largest standard deviation? Got 1, 2, 3, I don't know. Okay, it's exactly the same. So it's the same data points, just in a different order. So I've been using the blue signal, just shuffling it around, plotting it again, and it's the exact same data points. So it's the same data set. But if you think about looking at it, if you look at it from a standard deviation perspective, they also don't differentiate. Also from a mean perspective, same mean, same standard deviation, same thing. But there's a lot of like information in the blue signal, whereas the red signal is very, very random. So it's just like fluctuating around, not so much. And this is something we also often find when we measure behavioral time series, that they may have very similar sort of measures of dispersion, but one has a much more sort of temporal dependence or more sort of deterministic structure than the other one. The other one may be more random. So why the standard deviation is, and then in brackets, not a good measure of variability because it's still a good measure of variability, just doesn't capture the temporal dynamics. The standard deviation captures the magnitude of the variability, but not the temporal structure of time series. And this may be we therefore lose a lot of information in the analysis. And an increase in the magnitude of variability, so the standard deviation, is not necessarily a marker of poor performance. And I want you to think about the example of COP excursion again. So we're standing on a force plate. Our task is just to stand there. Our task is not to just stand as quiet as possible and to have our center of mass as closely aligned to a fixed point as possible, but our task is to stand. And what happens when you stand, there's a lot of swaying going on. It's not a bad thing. It's a marker of, it's a control mechanism of your body. So there's some sway going on, and this is not bad at all. So our using the deviation from this mean as an outcome of poor performance may not necessarily reflect the control mechanisms we have behind it. So if you say stand as quiet as possible, be as close to this fixed point as possible, then yes, it would be a marker of poor performance. But if they say just stand and don't fall, it's not, because you have a big base of support, and your center of pressure can be anywhere within your base of support, or let's say within a certain safety margin. And for your control system, it's enough to keep the center of pressure within the safety margin. And the standard deviation, of course, doesn't capture these dynamic patterns that may reflect control mechanisms based on feedback loops. So if we stand still, there are loads of feedback loops going on different levels, and the standard deviation doesn't capture that. Which now we dive into the theory behind it. So, okay, we're now in the domain of the complex dynamical systems theory. So I'll give you in the next, 20-25 minutes a complex systems account to movement variability. So first of all, our sensory motor control systems or physiological systems are dynamical systems. So what are dynamical systems? Those are systems that evolve or that change over time. We heard from Klaus in the morning that the brain, there's also dynamic going on in the brain. So the brain is, of course, also a dynamic system or subsystem of our physiological system. So it changes its state over time. We don't really want to look at it only from a stationary perspective. We want to see how it changes, what happens. A subset of dynamical systems are nonlinear systems where the changes in the state occur in nonlinear fashion, and a subset of these nonlinear systems are also chaotic systems, where there's also sometimes apparent chaos. And I think if we look at the brain, we do find that there are states of chaos where you can't make out a clear pattern that are also exchanged with other states where there's a very, very clear pattern, where we have very clear, for example, 12 Hertz rhythm, which looks very ordered. But then in other states, it's more chaotic. And the mathematical field of studies that studies sort of this temporal development, and they use differential equations for that, is also called dynamical systems theory. And we find these dynamical systems, and there's a lot of overlap between many other fields of research in biology, in sociology, in economics, and physics. So all of these fields, they deal with understanding how dynamical systems behave over time. What's the underlying patterns and mechanisms behind it. And further to being dynamical, the sensory motor control system is also complex. And what does that mean? So we heard the term complexity a couple of times in other domains today, but the complexity means that a system has many components, many subsystems on different levels, and these components interact with each other, and they are independent of each other. And these, on lower level subsystems, produce a macroscopic behavior on a higher order. What this means exactly, I will come to it in a little bit. But complexity in this case, and it's very hard to find a good definition of how you can define complexity, but in our case, I think this is very nice from David Vaillancourt and Carl Newell. They say that the complexity of a system increases with the number of its degrees of freedom. Degrees of freedom we'll talk about in a minute. And the number of connections between the degrees of freedom. So as you see, for example, in this figure, the one on the lower left, B, is not a very complex system. It has 3 degrees of freedom, and there's one connection between each of them. And if we add another degree of freedom, we can increase the complexity. So D is more complex than B, and if we here add more sort of connections between the degrees of freedom, so now this also talks to this and not just to this, and this degree of freedom talks to this one and not just to its neighboring, so then it's much more complex, and we can even add more to it. And the behavior of the system is very difficult to model due to the interdependencies of the degrees of freedom. Okay, this is very much on a meta level. Now I hopefully make it a bit more clear when we talk about what it means, what degrees of freedom are. And I would like to start with this guy. This is a picture that's not typically being used for him, but maybe some of you have heard from him. I know you from very different backgrounds, but this is Nikolai Bernstein. He has lived in Moscow and worked in the late 19th century, early 20th century. He was at the Moscow Institute of Labor. He was a physiologist, and he was a great developer of theory in motor control research. He only published in Russian and German, and not in English, of course. At the time, that was fine. And he did a lot of great work, really like in understanding the concepts of sensory motor control. In this year, 1967, his works have been translated and put together into a book. It's called The Coordination and Regulation of Human Movement. It's a very nice book and a really good basis for a lot of things. And he's being nowadays, well, even like since then, 20, 30 years later, he's a really he developed a lot of good theoretical thinking in the field. And he posed the so-called degrees of freedom problem. This is something that you should have heard of. And he said it's clear that the basic difficulties for coordinating consist precisely in the extreme abundance of degrees of freedom with which the nervous center is not at first in a position to deal. So that's his problem. That sounds, first of all, a little bit awkward, but I'll try and be a bit more clear about it on this slide. So he was not just a good developer of theories, he was also one of the first, or the first person, well, he contributed a lot to the measurement of movement using motion tracking. So he was basically one of the developers of motion tracking. And he used photography, of course. He tried to make high-frequency photographs of people performing any tasks. He also markered them so that he can track. And I'm not sure for the people of you who learned motion tracking, let's say 20 years ago, there was a lot of working by hand in tracking the markers, but nowadays it's much more automatic. But for him, it was also just handwork. So he just continued the photographs and measured the trajectories, for example. And what you can see here, and this is something he's been cited for very often, is a study he did with a blacksmith. And the blacksmith, for this blacksmith, using his hammer and hitting an anvil was a highly, highly overlearned task. So he's been doing that several tens of thousands times. It was a super, super highly skilled task for him. And what he found is that for this blacksmith, he can produce an extremely stable task goal. So he can hit this anvil in a very, very small sort of area when he's supposed to. So you say, okay, just hit the anvil here because you're supposed to hit the anvil, but when he just smashes any metal, then he also needs to do that. But on the other hand, his trajectories, his hand trajectories or arm trajectories during the movement to get there are highly variable. So from this highly variable starting position, he always manages to find the exact sweet spot where he needs to hit the anvil. And this is a very interesting finding. And often when I ask in class the students about the Bernstein problem, they always say something like it's a problem of variable movement patterns. They say Bernstein said it is problematic to be so variable. Of course, many degrees of freedom means there's a lot of variability going on, and this is problematic for the central nervous system. But I don't quite think it's so much the essence of this statement. For him, it's more like the question is how can we produce stable performance despite these many redundant degrees of freedom. Of course, there's some variability aspect that swings with it, but the question is how do we manage to have this to hit the sweet spot on the anvil when we're so variable in the execution. He doesn't say variability is a problematic thing. But nowadays, the idea, and people talk more about variability, and they're saying it's a consequence of this redundancy, but also stability of movement in a complex system, in a complex world where we have to adhere to many different changing constraints. Also, stability is a consequence of this redundancy. Another example by David Rosenbaum, maybe you've read his book as well. So this is also a picture of David Rosenbaum here on the top left. And he's making clear this concept of redundancy with another task and solution space. So if I would ask you to tip to touch the tip of your nose, you would do something like this. Everyone would do something like this. It's perfectly fine. That's a good solution to the task. But what he shows us on this picture is there is many other solutions to this task. And all of the solutions are equally valid. So it doesn't matter if you do it like this, if you do it like this, or if I come from here. It's also always a perfect solution of the task because I don't set any other task constraints. I ask the person to touch the nose with their hand, and all of that is a solution. There's no problem in doing it in any other way. So the nice thing with the redundant degrees of freedom we have, for example, in our arm, the kinematic degrees of freedom, is that it gives us the possibility that we exploit a range of solutions for any given task. So if we would have less degrees of freedom, if we were less complex, then we would have less solutions for a task. But having 7 degrees of freedom in our arm, meaning we can do it in many, many different ways. And this is something that's a very nice thing about this redundancy. So movement variability may reflect that. The solution space, so these different solution spaces also defined by the constraints. So the constraints internally are, for example, the range of motion of the individual joints and so on. And they are defined by task constraints. I can also set certain task constraints. Okay, I said touch your nose, but don't go behind your head. And then I set task constraints, reducing the number of, reducing the solution space. And you can also have external constraints. And then if you have a motor disorder, for example, I've done a lot of work with children with cerebral palsy, and they develop, for example, spasticity some of the times, and that does change the constraints. So they have a reduced range of motion, they have a reduced ability to produce fast changes of flexion, or extension, so certain motor disorders can affect the solution space, leading to a reduced solution space, leading to less potential solutions for a task. And what we find, and this is what you saw in Bernstein's example with the blacksmith that's hammering, is that the sensory motor control system does in fact exploit the solution space. This has been often termed as repetition without repetition. So if we repeat the same task over and over again, even if it's highly overlearned, it's impossible to do it the exact same way twice. First of all, because our internal systems are in a constant flux anyway. There's always changing internal constraints, so it wouldn't be possible. But on a measurement basis, you would not find the same solution for a task if a person does it twice, if you measure sensitive enough, of course. But then, also, not all solutions are equally desirable. So if I ask you to touch your nose like this, no, if I ask you to touch your nose, you wouldn't do this because it's not a very comfortable solution. So you would typically be somewhere in a solution space that's very comfortable for you. I'll show you another study in a second where this bin has operationalized. But if I, for example, change the constraints, and this is also something that's very helpful. So if I imagine you want to go out, open the door, you've got both your arms broken. What do? You may use your head. You may use your behind. Just push the handle. So this is also a solution. So you're flexible enough to adapt to changes in the constraints, and this is a very nice thing about this complex redundant system. So here's a short study, and it was nice. I talked to Paulina yesterday about it. She's working with the same task in her research, but in a little bit of a different context. And this task has been developed by Hermann Müller and Dagmar Sternat. Dagmar Sternl was a keynote speaker on the conference we organized 2 weeks ago, so it was very nice to hear about that in more detail. And just to give you another sort of take on this whole solution space concept. So they've developed a so-called Skittles Task, and this is an English pub game. So what happens in this game is that you have a little ball which is attached via a string to this pole, and people are supposed to hit this little target, this skittle, with the ball. So it goes like in a curved trajectory around it, then hits it. And they were using this task in a virtual environment, and then constraining it to really only 2 degrees of freedom. So this is then very, very much constrained. But what you can see in this picture, that we have different trajectories that are possible. So if we, I think we let go the ball here, and then it goes around like this, hitting the target like this. Or we let go of the ball here, it makes a little bit of a larger curve and hits the skittle here, or we have it like in an even more circular fashion. So all of these trajectories, and I think 2 is not a solution of this task, but this is very close to the task, but there's different solutions to it. And this solution space can be modeled using this heat plot. I think I'll just switch to the next one, where you can see, okay, oh no, I'll go back, so don't get confused by this. So these numbers here, they are related to what you can see in the trajectory. So the trajectory 1, and here on the x-axis we have the release velocity of the ball. On the y-axis we have the release angle. So trajectory 1 has a large release angle and a medium release velocity, and bam, it hits the target. Number 2 has a lower release angle and approximately the same release velocity, a little bit slower, and it goes around the target. It doesn't hit it. And the third one has a very low release angle, so it goes steeply up here, and also not a very high velocity. Well, it can be higher, I think, hitting the target here. So that's basically the 3 solutions modeled in this heat map. And what they found doing a modal learning experiment is that the performance error, which is what you see here, over time, so they had 3 blocks, and each block had, 360 repetitions. There's a learning curve at the beginning and the performance error, and then it flattens out eventually, but still a little bit variable. They found that there's changes in the release angle at the beginning, also flattening out to an extent, sticking to a similar sort of area. And they also think, in my opinion, like still some variability in the velocity. If you look at it from this heat map perspective, so the first set of trials on day 2, they are somewhere clustered here. There's a lot of variability in the velocity and also in the angle. And then day 4, they cluster around here, still a lot of variability. And on day 6, they're just moving or clustering here. The thing is, so everything that's white is a hit. Everything in this heat map that's white is a hit. So you see that the performance gets better. So on day 6, they're all in the white area. And what you also see is that this heat map, it has more space here. So it's a broader space, reflecting that in this area, the solutions are more sort of forgiving in any performance changes. So if you increase or decrease the release angle, it's still more likely that you have a hit in this area than if you're somewhere here, where only a very, very, very narrow combination of these release angle and velocity gives you an actual hit. And here you have much more space that allows variability. So typically our sensor motor control system finds a space that allows a lot of variability and still produces very, very stable performance output, even though the organization of our degrees of freedom is variable. So this is one of the findings of Dagmar Sternl in the Skittles Task. let's talk a bit more about complexity. So I already said we've got kinematic, or redundancies rather. So we've got kinematic redundancies in the arm. We've got, for example, 7 degrees of freedom, meaning joint axis. We got 3 in the shoulder. We got 1 or 2 in the elbow and upper arm. And we got 2 in the wrist. We've got 280 muscles in the whole body. And we often have more than one muscle per joint. So not one muscle is moving our joint and flexes or extends our arm, but more than one. They are synergists. They're working together. And we can use one or the other or both of them combined. Typically, we do that. We have many, many muscle fibers for each muscle. And we have a number of motor units that combine a set of muscle fibers, but we have more than one motor unit for every muscle. So it's not just muscle contractor or not, but we have many, many, many motor units that work together, that alternate, that perform work in a synergistic manner to provide the force output we need. And then we have neurons and synaptic junctions, which go in a very, very high number. So this is all super, super complex, the information processing. Then we get sensory systems. So those are motor systems and part of the sensory motor processing. And then we got sensory systems, which are also redundant. We heard in the morning that there's multisensory integration. We have many, many different sensory systems, and they are all very important. But we can, our sensory motor control does allow that some of the systems don't work as good as others. So you may be blind, but you still may be able to move. You may have hearing impairment, you're still able to move. There are certainly issues that come with it, but we can compensate. So due to the complexity of our system, we can compensate for errors or failures in some of the subsystems. And this is a nice thing. So let's now talk about the emergence of order. I tried to do that a little bit quicker. So how does order emerge in complex systems? This is self-organized. There's not so much top-down control. This is more like based on feedback and bottom-up control. And one wonders, okay, what's the driver of the self-organization? And it's typically driven by a task dynamic. And I think this flock of birds is a nice illustration. So flock of birds is also a complex system. There's many degrees of freedom, and every bird is a degree of freedom. And there's communication going on between the birds. So every bird has a couple of neighbors when they're flocking, and you do see what your neighbor is doing, or a couple of neighbors are doing, and your neighbors are seeing what you're doing. But there's no leader. There's not one bird like in the middle here who's saying, okay, we have to do this now. We have to fly as a group and make this specific pattern or that specific pattern. It just happens. It just happens to be, and it's driven by a global plan that every one of the birds kind of has in their mind. But even though they might not really understand the macroscopic behavior, they only know what their job in the system is. And all the degrees of freedom are enslaved by this global dynamic to produce this macroscopically ordered pattern. And in this case, of course, the task dynamics is a consequence of evolution of what happens in the birds. The degrees of freedom are controlled as a functional unit. They work in synergy. So they work together. They got the plan. They work together. They do everything they want to do in respect to, for example, the neighboring bird, and they communicate with each other, they see each other. Yeah, and self-organization is driven by feedback loops. So feedback loops, I mean, if I'm a bird, if I'm flying there, if I see my neighbor is very far away from me, I get closer. If I see my neighbor comes very close, has an effect of my flight pattern, I go further away from him. And this also happens on the level of degrees of freedom in the motor system. There's feedback loops. There's connections between the degrees of freedom, as you can see in the brain. What does it mean for human movement? So one of the classic models of self-organization in human movement has been this one. Do you all know this? Does anyone not know the Haken-Kelso-Bunz model? You don't know? Okay, I'll dwell on a little bit. So this is one of the classic models that describe self-organization, human movement. It has been developed in the 1980s by Hermann Haken. He was a physicist in Germany, and Scott Kelso. He was a neuroscientist from Ireland, and Scott Kelso was doing a lot on this work, on this finger movement and coupling. And Haken was more like in the theory domain of complex systems, but he was a laser physicist, so he was working with lasers. And they just tried to bring that all together. So they looked at this patterns of finger movement and found, okay, we can model individual fingers as oscillators. That's very nice. And we can, Kelso then found that we have very, very stable modes in this bimanual finger movement. We have an in-phase mode, where both our fingers move in the same direction, flexion and extension, so they flex at the same time or extend at the same time, or they move in an antiphase mode, where the one flexes and the other one extends, okay? So those are two stable modes. One is more stable than the other, and that's the in-phase mode. So you can model it like that. So in dynamical systems, it's always important to find a parameter to describe order. And for Haken and Kelso, it was the relative phase. And you also define stable modes in this order parameter. And they used 0 degree in phase and 180 degree antiphase. There are other stable modes you can learn. You can have like I don't know what, 270 degrees phase shifts or something like that. So this is also quite interesting that you can learn, but typically we can do 0 degree and 180 degree. And if we increase the cycling frequency, this is a so-called control parameter, we can lead that can lead to changes in the order state. So when we do this antiphase task and we have a very high frequency, then eventually we swap from the antiphase mode into the in-phase mode. It's impossible to stick onto the antiphase mode. This is something you can all try. When you do this, and now go antiphase, and now go fast, 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 fast. See, Uroš swapped. Okay. It's very difficult. You should also try and constrain your hands and only do it from the fingers, but you can do it with your hands as well. So there's many different ways of doing that. And we also did it for yesterday during the ice-breaking task where you had to do this one. That was also very difficult, wasn't it? What we can observe during this phase shift, there's a lot of fluctuations going on. So the system changes from one ordered state, getting into a state of chaos, moving to another ordered state. So the state of chaos is very short here, but this happens as well. Sorry, I'm now rushing a little bit, but I also want to get on to the data analysis bit. So now on this slide, what's the relationship between systems complexity and variability? There's a little bit of the summary. So we have a solution space. I showed you before. We've got different solutions for the same task. We have a solution space, and that allows to produce a stable performance even though our degrees of freedom are variably organized. So we've got different configurations in our arm segments to touch our nose, and still always is an equal solution of the task. The sensory motor control system stabilizes the task variable. So it's important that the task goal is reached, but we can still have flexibility on the level of degrees of freedom. So we can be variable, we can be flexible, as long as we produce a desired task goal. Large solution spaces, and this is also a nice thing, are very stable against perturbation. So if I have many, many solutions for a different task, and if something happens, for example, I've got 7 degrees of freedom arm, if by some means, I don't know, my elbow might be constrained if I have to wear a cast and can't move my elbow, I can still go on and open a door handle. It's not the typical solution I would use, but it is one of the solutions I can use to open the door handle, even though I'm constraining my system. And this allows for compensation. And the variability structure of physiologic processes is a marker of the complexity of the system. So we do find complex systems with many redundant degrees of freedom that communicate with each other, that they show a different variability structure. And now, what happens in aging or disease? Our constraints in the sensory motor control system change. We have changes in our sensory systems We may have visual impairments, we may have hearing loss, we may have tactile impairments, and so on and so on and so on. We have changes on the area of information processing in the brain, and we have changes on the level of the motor system, where we, for example, have a loss of muscle mass, where we have a loss of the number of motor units, we have more type 1 motor units, and so on and so on. Typically, and this is something that we see in older adults, is that they use compensatory strategies to reduce these changes, or to compensate these changes in the system. And that's often related also to an increased demand for executive control. There's less self-organization, more top-down control. These changes in individual systems, and this has been now 30 years ago that Lipsitz and Goldberger have introduced the so-called theory of loss of complexity with aging and disease. But that was in the domain of the cardiovascular system. But they said that we should maybe not look at very, very individual subsystems, but look at the human body as a complex system. And when constraints change due to aging, due to disease, there's a loss of the complexity. There's a loss of the functionality of individual components, but on the whole level, there's a loss of complexity. So these reductions in the anatomic complexity lead to changes in the function and the ability to adapt to changing task constraints, and in particularly stress. And what they did, they were investigating, as I just said, that the complexity of the cardiovascular system in a young subject and an old subject, what you can see here. And they were investigating a lot this temporal variability structure in the heart rate. And what they found that in a complex system, and in a younger adult who has a higher complexity in the system, there's a different pattern, different temporal pattern in the heart rate dynamics and in the fluctuations of the heart rate over time, or in the temporal structure of the heart rate beats, as compared to an old subject, where you have a lot of variability in general, but it's not such a, well, I would say noisy, but it's actually not a noisy pattern here. It's a complex pattern. It's not random. There's a deterministic pattern in there. Here's also a deterministic pattern, but it's less complex. So this is another interesting study from a study. This is a theoretical paper from Rita's from France. I've been lucky enough to also work with her a little bit, where she introduced also this loss of complexity and put it in relation to the dedifferentiation in older adults. And she also said that aging leads to loss of complexity in the neuromusculoskeletal system. On the components level, what you can see here, this is something we talked about. I again used the mouse. We have less degrees of freedom. We have less connections between the degrees of freedom. Generally, this is a less complex system than this one, of course. And on a behavioral level, we have, in complex systems, we have a complex pattern, a spatiotemporally structured pattern, as compared to systems with lower complexity, where we have here a very nicely ordered pattern. It looks like an alpha wave or something like that. But it's very regular and less complex. And these changes in sort of the complexity, they lead to a general reduction in the functional level. So we can compensate a lot, but eventually we will sort of hit the frailty threshold, and we can't really compensate this loss of complexity anymore, the loss of individual subsystems function. Okay, I think that's the last theory slide, and I have 30 minutes left for the methods. So complex dynamical systems can produce stable behavior. So this is nice. We can, even though we're very complex, so there's a lot of interdependence between our degrees of freedom, we can still produce an ordered state and can maintain that over time. A bit of a problem is that this doing that is producing this ordered pattern requires energy. So we as a system are dissipative. So we always have to eat to be able to do that. Otherwise, we would reach a state of very, very little complexity. That's death. And complex dynamical systems are adaptive. So order can emerge spontaneously from disorder. System states can change from one ordered state to another. That's a phase shift. That happens, for example, also when you change your pattern from gait to running. This is something, those are two different sort of coordination patterns, and they emerge spontaneously at a certain running speed. But you don't really do anything for it. It just happens to swap in one way or the other. Complex dynamical systems are robust, and this is nice. This is good news. They can adapt to changing task constraints, and they can compensate stress and failures of individual subsystems up to a certain point. Okay. Right. Methodologies. So, I want to show you two classes of methodologies for the analysis of variability structure. And the first one is entropy. And the second one is the field of fractal analysis. Starting with entropy. This is a term you might still know from school. So this is something that's been used in classical thermodynamics a lot. And it basically describes the irreversible changes of the internal energy state in a closed system. For example, following a chemical reaction. If you have a chemical reaction going on, you have two reactants that make a reaction, and then they release energy, and then they go to a state of lower energy or a state of higher entropy. That's similar, same. In statistical thermodynamics, that comes out of it is more like describing the possible the possible microscopic arrangements that happens after these processes on a microscopic level. And they also that's also what happens on a microscopic level, for example, and also in mixing processes. When you mix a drop of dye in a glass of water, then at the beginning, when there's a drop of dye in the glass of water, then it's a very clear differentiation. It's a very sort of deterministic system. You see where's the dye and where's the water. But then it starts mixing. It starts like forming patterns, and at the end, the dye is somewhere dissolved in the water, and it can have very, very, very different microscopic states. So again, this state of disorder at the end is a state of very high entropy. And in information theory, the entropy describes the level of randomness in a signal or time series. So the level of, for example, uncorrelated white noise. So all bit different fields. Sounds a bit weird, but in sum, what we can say and we can hold is that a high level of entropy describes a state of disorder or randomness. And a low level of entropy describes a state of order. Entropy can only be reduced. So the order can only be increased through interaction with other systems, meaning that in isolated system, there's only the development of entropy is only unidirectional. So if there's a chemical reaction, something is burned, the state of entropy decreases, the entropy increases. Oh, sorry, the errors. You had the wrong way. The entropy increases over time, and then it stays like that. And we have to add energy from the outside to decrease the state of entropy again. Okay, so what does it mean in time series analysis? I'll go back once. So I've got a little bit of an animation here, and this is something to showcase how entropy works. So can you predict the future state of a time series? So we've got three time series, top one, middle one, and bottom one. And if you see the first point, you've got this one here, and the last one up here. If I go a couple of points in the future, you see that in the top one, everything stays at the bottom. In the middle one, you see this pattern, and in the lowest one, you see this pattern. So can you predict what's coming next? Well, just go on. So it goes on. This one stays here. This one goes up and down, and this one goes down here, and go on and go on. And what you can see is that the top one and the middle one, they are easily, at some point, you recognize the pattern, probably at a very early point, and say, okay, I do know from the current state I am what happens in the next state. At time point t, I can say what happens at t plus 1. In the panel at the bottom, it's very difficult. It's basically impossible because it's random. So you can't really say anything. So entropy actually measures or quantifies this predictability or unpredictability or randomness in a time series. So it looks for some repeating patterns or measures of entropy and gives you at the end a number of this determinism. And it's not such a trivial task because these patterns might not always be so easy, like you can see here. They can also be more complex. And then, it may be very difficult to find these repeating patterns. So this may emerge at different timescales. So we may have different, what you see in the brain, you have different overlapping patterns, and looking for order in that may not be a trivial task. So quite a while ago now, Pincus has introduced the measure of approximate entropy to obtain a measure of this repeatability or temporal sort of deterministic dynamic structure of a time series. And in this algorithms, we need a couple of things. We need a couple of things. We need, first of all, a time series, of course. He suggests to have a very, very long time series, so at least 1,000 data points. So if we look at gate studies, this may be sometimes very difficult because people had to walk 1,000 steps to do that. If we look at the temporal dynamics of the gate patterns, so this may be very difficult. But for things like, and there may be some recognition of this one. This is the COP path I showed you in the beginning. For these measures, it's a bit easier. So we have a time series of data length n. We have a tolerance radius r. So this is typically chosen at 0.1 or 0.25 times the standard deviation of the entire signal, but maybe it's good to try a little bit around and use other values for that. And a pattern length, which is typically 2, but can be more, and optionally a lag. But I want to show you now how this works, because it sounds like a weird thing to do, approximate entropy. Okay, I want to measure the determinism in the signal, but it's actually not so difficult when you look at it. So again, I reduced the signal to a very short little snippet in the beginning. I used only the 10 first measurement points of the signal. So we have in this COP movement, we start by minus 0.133, minus 0.135, minus 0.129. So it goes up a little bit and then it goes down again, and so on. What you do is you split the time series into short vectors of length m. So m is 2. And my short vectors are basically capturing the first 2, so 0.133 and 0.135, that's here. And I capture the second one and the third one, so that's 0.135, 0.129, and I repeat that over and over again until I have 9 vectors with length 2. And for each vector, I then count how many of the other vectors are similar or within the tolerance range R. So this is my first vector. It's 0.133 to 0.135. And the blue shaded area is the tolerance around. And now I put in all the other vectors that are on here, and I can see that 2 other vectors, so those that are in red, are actually within the tolerance range. They are within this range of, I consider them as similar. And then for this condition, or for this vector, I compute the conditional probability. For example, p equals 3 out of 10, so including the self count. So we've got 1, 2, 3 out of these 10 vectors. Oh, we have 10 vectors or 9? So we've got 3 out of 10 that are actually similar, and that's nice. And what happens next? That's not yet the measure of the entropy. We do the same thing as above for m plus 1. So we not just have vectors of length 2, but we now just have vectors of length 3, so 3 consecutive numbers. Again, I have the 0.1, 0.2, 0.3 tolerance radius, and I check again how many of the other vectors n plus 1 are similar. And here I can see, it's only 2. So this one, who was previously similar, is now not similar anymore, because if we look at m plus 1, it doesn't fit in the tolerance level anymore. We compute the natural log of likelihoods for L1, 3 out of 10, for L2, 2 out of 9. We do the same thing for all of the other vectors. So if we have a time series with tens of thousand data points, it's lots of computation going on, a lot of repetition. But we do the same thing for L1 and L2 for all the other vectors, and divide the number of vectors and divide by the number, so this log likelihood by the number of vectors to obtain phi1 and phi2. We then only subtract phi1 from phi2, and then we get a measure of approximate entropy already. The assumption is that when signals have a very similar or deterministic pattern, the likelihood of finding similar vectors with length m plus 1 is roughly the same as the likelihood of finding similar vectors with a length m. So it wouldn't change so much if we look at it in terms of vectors of length 3 as we do when we have vectors length 2. And that's nice. So if they are both very similar, or if they're both exactly the same, if they have a repeating pattern, then our measure of approximate entropy will be close to 0. And for uncorrelated random signals, for example, white noise, the entropy will be close to the Euler constant. That's because of taking the logarithm and so on. Yes, please.
Subtract phi2 from phi2, do you mean phi1?
Yes. Subtract phi2 from phi1. Yes, thanks. We've got another one, which is called sample entropy. Came a little bit later. We found out that, or they found out that approximate entropy is very sensitive to the length of the data. So if you have very long data sets, it really influences the outcome of approximate entropy. So you should always normalize it. And it's also very sensitive to this initial parameter selection. So how long you have it and what's your tolerance radius. And sample entropy is a little bit more robust. And it can also be used for shorter data sets, which is a very nice thing, because now you can start working on gate data over time. Again, the steps are very similar as for approximate entropy. However, in this case, we don't count self-matches. So if we look up here, we only have 2 hits, and if we look down here, we only have 1 hit, because the self-matches, they can bias the results very much in short data sets. And then at the end, you take the logarithm of the sum of conditional probabilities rather than the log of individual probabilities. So meaning that you first of all count all the probabilities together and then compute the logarithm, and in approximate entropy was just different. So not so different. All of these algorithms, they are good implementations. For example, if you're using R, if you're using MATLAB, they are ready-to-go packages you can just use. The only thing is you have to choose wisely your initial parameter selection. I just wanted to show you this for showing that, like, the math behind is not so difficult. There's another thing that's been coming up lately, and it's called multiscale entropy. So you might have come across that when reading some papers in the field of motion analysis. So multiscale entropy has been introduced. And this is very interesting, because it now considers the entropy of the system on multiple time scales. So we don't want to look at it from times on the level of very, very short time scales, really looking only at the fluctuations that are going on, but really looking at the whole signal in general. And what you get then is a picture that's more like this here, and I'll show you what that means. So timescales mean that you sort of start filtering the signal, or scaling the signal in time. Meaning you take as a first scale, or scale 1, all the individual data points. So you do the sample entropy on each individual data point, x1, x2, x3, x4, so make your vectors, calculate your conditional probabilities and so on. And then you do the same thing after averaging 2 consecutive data points, so x1, x2, x3, x4, and just compute the average. So you have reduced sort of the the temporal information in your system. And you do that on many, many different scales. Then patterns emerge. So what we see here, the first data point here, so we have a comparison between the COP data and white noise. So white noise is just really a random signal with mean of 0 and standard deviation of 1, or you can have any other mean or standard deviation, but it's a random signal. And what you can see here is that at low timescales, which is just a normal measure of approximate entropy or sample entropy, we have a very high entropy for white noise and a very low entropy for the center of pressure. So this is what we expect. In center of pressure, there's a lot of determinism in there. And in white noise, there's a lot of randomness in there. So we have a high entropy in white noise in short timescales and low entropy in the center of pressure in short timescales. But with increasing timescales, you find that the entropy increases in the center of pressure and it decreases a lot in white noise. And this sort of pattern, has been shown previously. So scales with high entropy over most timescales are considered more complex. So if you look at this pattern, this is really a pattern of more complexity because most of the timescales have a high entropy especially the higher timescales. So this has been by Costa and Goldberger, who wrote this paper. They have defined that as more complex patterns. I want to show you some studies. I think I have a little bit of time left before going to fractal analysis. So in this study, the authors used approximate entropy to detect the effects of a secondary cognitive task on postural control in healthy young adults. They had 30 young adults, healthy, and they used a sensory organization test. And in the sensory organization test, participants were standing, so they didn't have, they either had their eyes open, normal vision, or eyes closed, and they had different sort of sensory feedback in this task. And what was measured was the center of pressure, medial, lateral, and anterior posterior direction, and the outcomes were the approximate entropy and the root mean square error. And they also performed the dual task on top of that. So what they found is that dual tasking led to an increased randomness of the center of pressure in anterior posterior direction. So they actually found a higher approximate entropy as compared to single tasking across all conditions, and no effects were found for the root mean square error. So they concluded that low entropy in single tasking is potentially due to the task constraint to stand as still as possible. So what we typically expect in or what we sometimes find, that's not all of the times, is that standing in a single task situation actually leads to a higher randomness in the signal. But in this case, it did lead to a low randomness. And what they actually thought or found in the end is that it was probably due to the task constraints that they actually told their participants to stand as still as possible, as close to a fixed point. Don't move at all during the standing. And the dual tasking in this case may reduce this constraint and release the degrees of freedom. Hence, they found a little bit more randomness in their signal. Another study on Parkinson's, it's on the dynamics of postural control in Parkinson's disease with and without symptoms of freezing of gait. So they had 32 patients with Parkinson's disease, 15 of them were freezers, and 24 of them were healthy subjects. They had 32 patients with Parkinson's disease, 15 of them were freezers, the other 17 not, and they had, on top of that, 24 healthy controls. The task was to perform quiet standing with eyes open, eyes closed in single and dual task situations. And they measured the center of pressure again. And what they had as outcomes was the path length and the sample entropy. And what you can see in the top figure is the COP path for a patient with Parkinson's disease. And down in the bottom figure, you can see the COP path for healthy control. What they found is that Parkinson's patients exactly display larger path length, so the total path length. That would also be related to the standard deviation in both directions. But they did find that freezers or Parkinson's patients that showed freezing of gait showed a higher regularity in their pattern, so less randomness or complexity as compared to non-freezers. Randomness is not the same as complexity, but so let's say freezers showed less complexity than non-freezers, and non-freezers showed less complexity than healthy subjects. So healthy subjects had the highest complexity in their COP movement, and freezers had the lowest complexity, meaning more deterministic pattern. So, and they said that this higher regularity in COP path may be a signature of the deteriorating control and lower ability to adapt. In this cases, then also lead to the lower ability to adapt to perturbations and then leading to higher probability to fall, for example. And I'll skip this one. And I'll come to one last, so the last class of measures, and I try and be a little bit faster, but it's fractal analysis. So this is another set of measures that estimates the complexity in time series, and it's not so much about the deterministic and repeatedness of patterns, but it's more about in time, but it's more about the self-similarity of signals on different time scales. So, do you know this one? Probably, huh? So this is a very popular example for fractals in nature. And why is that?
Because you can zoom in and
it looked the same, yeah. So it looks the same on a macroscopic scale, and it looks the same on a next scale, and I think Romanesco has 3 scales, or self-similarity in 3 scales. So if I look at the Romanesco as a whole, it looks like this knob, and if I zoom in on one of these little ones, it looks exactly the same as the big one, or not exactly the same, but very similar to the big one. And if I zoom in on another level, then it would look again the same. So it doesn't matter what scale you look like, it looks very similar. And this we find also in human motion. Behavioral processes can be also very self-similar on different timescales. And one of the examples I have here is the COP data. Again, you see the COP data on a timescale of 60 seconds, and you see the COP data on a timescale of 6 seconds. So zooming in, I do find that the pattern that's displayed here is also somewhat similar to the pattern that's displayed here. Not exactly the same, but a similar sort of, yeah, overlap between high and low sort of fluctuations. And this use of fractal scaling, or this picture of fractal scaling, can also be analyzed to find whether there are deterministic patterns in the signal. So what's been typically done to do so is so-called detrimental fluctuation analysis, where you integrate the signal, you get a profile. This is integrated white noise. This is then just becomes a random walk, a Brownian noise. And then you pick short segments, for example, size t equals 10, and then you calculate, so you can't really see that very well, but there's very little linear models. So always with 10 successive data points, I fitted linear models. And then from these linear models, I calculate the root mean square error. And then I do the same thing for increasing window sizes. For example, t equals 100 and t equals 300. So, and always I get for these little linear models, I get a root mean square error. And these root mean square error, they give me some information about whether or not there's a different amount of fluctuations going on different timescales. So I then create a log-log plot. So I take the logarithm of the window size and I take the logarithm of the root mean square error, average for all the windows, and plot them against each other. I then fit a linear model, and the slope coefficient of this linear model basically reflects the self-similarity. And white noise, so up here you see white noise. has a very, very flat power spectrum typically, and also has a very small exponent. So there's a lot of noise on a lot of high RMSE on very low time scales, but the RMSE doesn't increase so much because it has a very flat here scaling exponent. On the other hand, if I have pink noise, I have a scaling exponent of roughly 1, and if I have the center of pressure movement, I just showed you previously, then I have a very, very steep scaling exponent, speaking of very, very high self-similarity on different time scales. And this is the gate data I showed you previously. So I had my 150 steps. I computed the scaling exponent for the 150 steps for the stride time intervals, and I found that we have a scaling exponent of 0.87. White noise is 0.5, so random signal has a scaling exponent of 0.5, pink noise is 1, and our stride time fluctuations have 0.87. So meaning there is a certain deterministic pattern or a certain fractal pattern in the gate dynamics of human movement. So it's not just white noise, it's not just randomness we measure there, but there's a pattern in there. And this pattern actually changes with agent disease. I do not have a study on gait, unfortunately, but Jeffrey Hausdorff has done a lot on fractal dynamics in gait, so it probably rings a bell if you're in Parkinsonian research. You can read up on that. Actually, so I want to finish up with one of our own studies where we measured fractal scaling in bimanual force control tasks. So we had younger adults, we had cognitively healthy older adults, and we had older adults with MCI. They were both age matched, and they were performing a bimanual vision motive force tracking task where they had to trace two little square boxes. They were basically setting the target force, and they had to follow these target forces with their own force levels. So squeezing to force transducer, meaning ball goes up. Releasing force transducer, meaning ball goes down. And what we found is, or what tasks we did, amongst others, is we either had them to produce a constant force with both hands, so meaning they squeeze both force transducers at a level of 12% of their maximum voluntary contraction, or they had a task where they had to produce a constant force with one hand and an alternating force with the other hand. So this is like an asymmetric task. Which is a bit difficult because there's some interhemispheric communication going on, and typically we find, not typically, but sometimes we find that there's some bimanual interference, or just that the pattern of this production of a constant force may be disturbed when the other hand has to produce an alternating force. We measured the time on target, we measured the bimanual coupling, which is the cross-correlation coefficient of the signals, and we measured the DFA scaling exponent, so we did detrimental fluctuation analysis. And we found that there was similar performance deterioration for all groups from bimanual constant force production, so when they did both in one hand, to constant force production in the asymmetric conditions. So when they had to do it in an asymmetric way, one is doing the sine wave, the other one is doing constant force. This leads to deterioration in the constant force production. What we also found is that there was a larger increase in the scaling index for bimanual constant to this asymmetric in the younger adults as compared to older adults. We didn't find so many difference between older adults and MCI, but meaning the effect that this asymmetric task has on the other hand was much higher in the younger adults. This is something we attributed to an increased crosstalk between the hemispheres in younger adults that also sort of leads to a matching of the complexities between the two hands, because sine wave force production has a very, very high scaling index, and a constant force production has a rather low scaling index. It's more sort of more undeterministic, more random, but when we do it both at once, it very much affects the hand in younger adults, and not so much in older adults, and this may be due to sort of reductions in the interhemispheric exchange of information. So sorry, the end was a bit of a rush, but I want to really read down my take-home messages. So we learned, or we talked about, that sensory motor control systems are complex dynamical systems. And we also heard that rich solution spaces are very important when, for stable behavior when constraints change. So rich solution spaces and redundant degrees of freedom are important for compensatory function. Statistical measures of dispersion, like the standard deviation, capture the magnitude of variability, but they don't capture the temporal structure of variability. Measures of complexity, for example, entropy or fractal analysis, they can capture different aspects of complexity of the signal. For example, they capture how much randomness there is, how much determinism there is, whether there's self-similarity in different timescales. And we actually find that different control mechanisms actually affect these signals, the randomness or the self-similarity, since we, for example, might integrate feedback loops differently when we have a more complex system. Changes in these markers are attributed to changes in the complexity in sensory motor control due to changing task or intrinsic constraints. So for example, with aging, we have a reduction in the complexity, and that may also be found in the signal. There are other measures for really thinking about how you can relate reliability to performance, also not just in a temporal way, but also in a sort of, let's say, spatial way by looking at the system as a whole, thinking about how many solutions there are and how big your solution space is. This is like Dagmar-Sternhardt's study I showed you in the beginning, so such things are also possible. But there's a variety of measures for the variability. Yeah, that's it. Those are my references. I'm sorry for the rush in the end, but time is up and I'm open for questions, of course.
Thank you so much, for a super interesting talk and super important. Are there any questions? Can I start? But I wanted to be very pragmatic here, or very practical, perhaps, just from the analysis point of view. If we take, like, I don't know, students who are coming from the field of psychology, or students who are coming from the physiotherapy or kinesiology, movement science in general, like, what would be your suggestion of what kind of measure next to mean and standard deviation that we usually calculate out of mean reaction times and then variability, or mean gate speed and variability of it, like of what you've shown here, would be your recommendation to start with? Because usually we do just these basic calculations and we don't care that much about all the atrophy and other. Yeah, okay, I guess being pragmatic is nice, makes sense. It's a little bit difficult because it depends a lot on what data you have, what you expect to be in there, but I mean, this people use very much still the measure of sample entropy. This is something, approximate entropy not so much anymore, but sample entropy is something that's been used like extensively in a lot of studies on gate dynamics and as well as detrimental fluctuation analysis. So these two are basic measures. Often they are used both at the same time in the same study. They reflect different aspects, but they still have very similar outcomes. And you get very good implementations in R. So there's a lot of packages pre-ready in R that gives you an implementation of these algorithms, so you don't have to do it yourself. It's nice and easy and set to go. So I would say sample entropy is something which is always a nice measure because it also has a clear interpretation. What's important is always to compare the results to other measures. If you, for example, you can simulate white noise and then you compare it to what is really white noise, what is a purely random process, and what happens if I have a process like a physiological behavioral process, which is then not random. How does it change its complexity? So compare it to a very deterministic pattern, maybe like a sine wave, and compare it also to white noise and see how this changes. So this is something to get a good, better hang on what the results mean. Okay, but then when you do calculations, that you basically say, okay, that's the mean, that's the standard deviation, coefficient of variance, and then you have some extra, or you always select different variability measures that you would be analyzing them. For instance, for gate speed, you take something else then, always.
Yeah, I would also look into literature, what other peoples do. Again, for Parkinson, Jeffrey Hausdorff is a really good starting point. He's done a lot of research on variability structure in Parkinson's disease. So I would have a look there. But again, sample entropy is one of the most used measures, so that's probably the starting point. Next to certainly all of these classic measures, so standard deviation, always report like the magnitude of variability. But understanding like the control processes from a complex, understanding it from really the control mechanisms perspective, this is also nice. You can. Yeah.
A new measure now.
Thanks for the talk. I think I understood it. So
I'm glad.
My question is also maybe pretty pragmatic. It's also about the interpretation of the entropy.
Mm-hmm.
So is it all? Is there like something like how to interpret effect size? Something like a rule where you can say like, oh, this is like what you did with pink and the white noise, like a guidance.
Yeah.
How to interpret it, or is it always only possible to compare two conditions?
Yeah, that's a good question. There's a technique called surrogation. So what you typically do is you take the time series you have and surrogate it. That means either you just make a random signal out of it, just randomly order it multiple times, then compare it to this one, or you leave some of the frequency patterns in there. So you make another signal out of it with some similar frequency components, and then compare it to this one. And then you see, okay, this is actually something that affects the complexity, the self-similarity of the signal, not just because of the frequency components. So this is something that's been done typically. Yeah. There's a good book from Nick Sturgeon. I had one of the studies where it's like a really, really great introduction. All of these measures, a lot of the measures slides were from there, and the surrogation is certainly something you do.
We can ask you to share this information. Perhaps we can post it for everybody else, so that would be helpful. Great. Any questions? Yes.
Great talk, thanks.
Thank you.
I think it's all about variability. I was wondering how much you can actually also dive into intra-individual variabilities. Because still most of the times I see large group comparisons, but if the focus is the variability and then you average across a large set of participants across groups and so on, you lose that fine-grained information that maybe we want to be after.
Yeah, that's a tough question. I like it. It's hard. Yeah, I mean, this we just talked about is about time series. So it's really about the macroscopic behavior of a system and how that depends on the temporal dynamics. And of course, if you have large populations, if you want to investigate the inter-individual variability, this would not be possible because then there's no temporal sort of structure that's in there or dependence of the individual upon any other individual. So this is like nothing I could order in a certain way. But yeah, I also think I agree with you that it's averaging and standard deviations is nice because you can find group effects, but what does it mean on an individual level? This is very, very difficult because if we come from the other hand, from the other side, and we say, okay, we want to, for example, classify between mild cognitive impairments and healthy individuals, and we find certainly group effects in some of the measures, and it's nice. So the means are different and the standard deviations are high, so that means we can classify, I don't know what, 52% correctly or something like that, but not more. And then you think, okay, what does it tell us? We found difference on a group level, but we can't, on an individual level, make an assumption about how this really affected their behavior, just as a consequence of the MCI. You can make differential diagnosis, taking many, many things into account, and then your model may become more accurate. But yeah. I think this is something we should consider more. Sorry.
No worries. Another question? A comment?
A comment to your question, but maybe I missed it.
Oh yeah.
Your answer or your question. I would say that all measures of integration
intra-individual variability. So let's address intra-individual variability in different levels, so like the coefficient variation or by standard deviation or by entropy measures, and of course you then summarize them on the group level and compare the group, but what you compare is the variability between groups. And I think it's important that before you start writing the paper or analyzing results, make sure that you are interested in the variability of the performance or in the structure of and so as Julian described. And there are different ways to address it, but I would say that are all measures of intra-individual variability. So last time I said that word today.
Thank you, Claudia. Any other comments, suggestions, questions? Then thank you, Julian, once again.
Thanks again for having me.
Very good.
Thanks. Very nice. Thanks. Oh, awesome.